All right, so I'm going to share my computer. Can you guys, somebody turn off your audio and tell me that you can see the agenda?
It works for me.
I can see it.
I can
Thank
see
you.
it.
I can see it.
Thank you. Okay, so here's the agenda. So for my PLTW access, oh yeah, this one goes here. I know I've spoken to several of you about that. And if you don't have your credentials, just email me and let me know and I can send it to you. But I'm going to send it to your SRVUSD Gmail account because I don't have all the credentials in text formats, so it's much easier for me to take a small screenshot of your user ID and send that to you. Okay. Okay. How about Schooloop versus Google Classroom? Well, historically, Schooloop has been the central place where everything is located, and I'll continue to put stuff in Schooloop. That's where the gradebook is, and of course this semester it's all pass and no mark, or pass for I'm sure everybody, but I still need to have that. But I'll more and more be doing please see assignment details on Google Classroom rather than putting the details in here, so that I don't have to write it twice and have more opportunity for errors. So that's that. Okay, in terms of the Google Meets going forward, I think I'll have one per week unless there's strong interest in having more of those. The next one will probably be next Tuesday at 1 o'clock. We're going to start a new unit, structural engineering. I'll talk about that in a minute. And then today we're going to focus on this thing called the Centroid. And again, just chime in if you have any questions. Okay, so what about this new unit? We're going to leave behind, out of necessity, the CuPy robots, and we're going to move on to this new unit. This is a unit which I usually do in the fourth quarter like this because there's a little more math involved. So folks who are in geometry, say, have an opportunity to see some trigonometry before we go into this unit. So structural engineering, it's a subfield of civil engineering, building things like bridges and buildings. And 2.1 is statics, and basically that means make sure the bridge doesn't fall down. Quick and dirty definition of what we'll be doing there, using Newton's laws to make sure that everything's in equilibrium. Any questions? Okay. All right. If you came in late, I apologize if I had 2 different times for the start of the meeting, but I'm recording this, so you can access what I haven't talked about yet. Okay. And then we'll go into material properties. So this deals with things like make sure the material for the bridge can hold up, doesn't break. And also, almost as importantly, make sure that we don't use more material for the bridge than we need to, so we can minimize the cost. Today, we're going to talk about finding this thing called the Centroid. And not being a structural engineer myself, while I understand what the Centroid is in the abstract, why would it be used? So I've tried to figure out that and done some research. They don't really talk about that too much in the my PLTW, but so why do we care about this thing called the Centroid? Well, we'll define the Centroid in a minute, but just very briefly, what it is, it's a point on a 2-dimensional plate, if you will, and it's sort of the center of it. It'll coincide with the center of mass if it's of uniform density, but it's the center of it. So what if you had to balance this? Say you had a plate in the shape of a triangle like this, and you had to balance it on a column. So you can imagine some version of this could be the case for if you're building a structure. Well, it turns out that you would place it on the centroid, which is located on this plate somewhere. But for a figure like this triangle, it's not obvious where that is. So we'll talk about that. The other one is related to, this is again, example 2 of why do we care about the centroid? What it means is that we can replace a distributed load with a concentrated load. So we haven't talked about the definition of any of these things. So let's do that briefly now. So a distributed load would be shown down here. We've got this piece of wood. It's a beam. It's a horizontal piece of wood maybe. And what this W function represents is the sort of the weight per unit length that's pushing down. So you can see it's got big arrows on the left, smaller ones on the right. So it linearly goes from some value W0 down to 0. And we'd ideally like to, let me do it this way. We'd ideally like to replace this distributed load with a concentrated load. So here's our distributed load right here, pushing down more on the left than the right. To ease our calculation, we'd like to replace it with a concentrated load at a specific location, and that location is the centroid. So that's another reason why we might want to learn the centroid. The value of this replacement force here, turns out it's the area under the curve here, but we're not going to deal with that. We're just going to talk about the centroid. Here's another example of a concentrated distributed load. It's this curve over here, and here's our beam. And we would like to replace it with a concentrated load right here to replace all this complexity. And it turns out that at the centroid, we can do that. So that's why we might want to calculate the centroid. Okay. All right, if there are no questions on that, then I am going to move on to the MyPLTW business. So here's unit 2. That's where we'll be working. And we'll start out with statics 2.1. Career field description, we're going to skip that. And we end up with centroids. The MyPLTW interface can be quite good, but occasionally it's a little quirky. And so they tell you to come down here and check out these resources. And what I like to do, since if I just click centroids here, it's going to take me to some location. It's not obvious how to get back to this location. So I like to do right click, open a new tab, and therefore I can go to that centroids location. So I'd recommend that technique. Okay, so let's just go through here. This is actually quite good, so please read it if you haven't already done so. And I'm just going to hit the highlights. So for a plane with a lot of symmetry, like a square or a circle, they have symmetry axes. For example, coming along here, if I rotate this square about this vertical axis, then I get the square back again. So that's a symmetry axis. And there's a diagonal one and a horizontal one. The centroid is always going to be at the point where all of those symmetry axes intersect. And similarly for the circle, only 2 of them are drawn here, but there are an infinite number of symmetry axes on a circle. So it's got the horizontal and the vertical ones, and that's where the centroid is going to be located. So highly symmetric shapes, they're pretty easy to calculate this quantity. And how about for a rectangle? Well, if we want to find the location of the centroid with respect to this origin down here in the lower left-hand corner, then we just find the axis of symmetry where they intersect is the centroid. Hopefully you can see that that's just halfway over, so it's b over 2 and h over 2, where b is the horizontal length here and h is the height. So just right in the middle, just like you'd expect. As we move on to things that are not so symmetric, we have to use a different method. And if you were taking this class as an undergraduate at the university, you would derive this equation here. It uses some high school level calculus, and I'd encourage you to check it out if you're taking calculus. But it turns out that the centroid of this right triangle is a third of the way out of the base and a third of the way up the height from the right angle vertex. And you can derive that using calculus. We're not going to do that. We're just going to keep this in our notes and know that if we have something that's shaped like a triangle, then we can just use this formula. Similarly, for a semicircle, this does have an axis of symmetry, sort of the vertical axis in the middle. So it's going to be definitely on that axis. But the question is, how far do we go up? And again, using some basic calculus, you can derive that the location of the centroid in the y direction, which is vertical, is 4 times the radius divided by 3 pi. So just something you need to take as a given, or if you've had a little bit of calculus, then you can derive that. Okay, so what if the radius here was 2 inches? What would we get? Well, we just put it into this formula here, and we'd find out that it's 0.8 inches above the base of this semicircle and on the axis, vertical axis of symmetry right in the middle there. Okay. All right, so that's kind of the warm-up. For the what you're going to be doing is calculating it for more complex shapes. And it turns out for more complex shapes like this, we can use the results above here and kind of decompose this figure, find the centroid of each of the individual uh, subfigures, and then add them together in a special way. So how would you find the centroid of this shape? Well, I guess it would be on the symmetry axis here, but it's not clear how to get that. So we break it into the shape into simple shapes, and then use the centroid's formulas on those simple shapes. So let's do that. By the way, just kind of thrown in here, I'm not sure why it's here. Just the centroid is the same as the center of gravity if you have a symmetric shape like this, or if the plate has uniform density. They're one and the same, center of gravity and the centroid. Okay, all right, so let's go to the focus of stuff we're going to do today. So these equations here are the way that you can calculate the centroid of a more complex shape. So what do the sigma mean? Capital sigma, many of you already know because you've taken math on it. In case some of you have not seen this as much, let's see. I want to point out what this sigma notation means. This is the Greek letter capital sigma. And if it basically means sum up all the stuff to the right. So here I've got summation of f, and it's got a little I subscript. So this would mean f1 plus f2 plus f3, and we would go on until we're finished summing it up. And when we stop will be known from the context of the problem. So that's all that means. Rather than say sum all the forces f sub I in words, we just have this symbol. So it's kind of par for the course for math, right? So that's what the capital symbol sigma means. Okay, as we come back here, so here's our formula for the centroid coordinates of a more complex shape. So we break it up into smaller pieces, as we'll do in a minute in this example, and then we sum up all the x centroid values, and we weight them by the area of the figure that they're the centroid for. And then we divide by the area. So this is kind of a weighted centroid based on how big of area it represents. Okay, let's go ahead and do this problem. So there's two methods. There's the additive and the subtractive. So this is pretty good. So here's the picture. We've got this object that looks like this. And I'd encourage you as you're doing these assignments to draw these pictures out nice and big like this. So let's go to the next step. And what they're doing here first is they're breaking it up into three different uh, regions, all of which we know the centroid for: rectangle, square, triangle. And so region one is the tall, skinny rectangle. And so they're just getting the area. Remember, we have to sum these areas in the denominator. So that's 18 um, square inches. And then shape two is the triangle, half base times height. So its area is 4.5 square inches. And finally, the square here, region three, and it is 9 square inches. Okay, remember that goes in the denominator. Adding all those up is right here. Okay, let's go on to the next one. If I click this little button. And then what we're supposed to do is find the centroid coordinates for each of those subfigures that we've just created. So shape number one, it's going to be right here. Shape number two, the triangle is going to be a third of the way in from this right angle vertex. So it's right there. By the way, this is a symbol for the centroid, and you should use that on your diagrams. And finally, for the square, of course, it's right in the middle. So I'd encourage you to draw something like this as well. And now that we have that information, we need to, this is a really important point, we need to translate those values with respect to some vertex or some coordinate system. The origin is down here in the lower left, and you can see they're getting all those x and y coordinates for the centroid with respect to that point. So remember, it was 1/3 of the way in for the triangle, but the triangle has a base of 3, so it's actually just going in 1. So 1 plus that 3 gives you 4. And same for the y coordinates. Yeah, it has to, they all have to be with respect to this particular, a origin point that you choose. And typically, it's the lower left corner. Okay. All right. You might have to go through this, a couple times on your own, but hopefully this is kind of a good catalyst for you, getting you there. So again, as you do these problems, I'd recommend that you make a nice little table, and these calculations aren't conceptually that difficult. It's just they're kind of messy. And so the really useful skill you can develop by practicing on this assignment is how to maintain a very lengthy and messy algebraic calculation. So for shape one, we know the area, we calculated that. We know its centroid component, it's 1.5, and then the product of those is 27 inches cubed. And then we had the areas here. Oh, this is the y values, so the areas are the same. And so these are all the individual components of the numerator that we're going to sum up. Question? Okay. And so again, sigma a sub I x sub I is, just add them up. You see the plus sign between there, sum them up, and we get 85.5. And again, that's adding up this value, and this value, because that's what our equation says to do up here, is to sum up the numerator like that. Okay. And then we sum up all the areas here. So 18 inches squared plus 4.5 inches squared plus 9 inches squared gives us that value. And then we stuff it into the equation, which is right here, and we get that it is at 2.71 inches in from this lower left vertex. And you can see it is on the axis of symmetry. It's kind of a diagonal, which makes sense. Any questions or comments on that? Okay, so that's the additive method. There's another method called the subtractive where you do pretty much the same thing, but there's a subtle difference. For the subtractive method, we would take that same figure and we would make the whole thing and we'd add in a little chunk here. So we divide it into the whole thing, and then we would subtract away this by giving it a negative area. So shape 1 is a square, shape 2 is the triangle with negative area. And yeah, since the area is being removed, it is noted as a negative area. Kind of counterintuitive. We don't typically think of a negative area, but that's the way we want to look at this. So this would be the subtractive method. And then we just turn the crank. We find the location of the centroid with respect to each little subfigure. And here is where they get it with respect to this origin point here. Really important that you do that. And then they turn the crank and they get the same answer. Okay. Finally, so that's the calculational business. Finally, there is one other area where you might have an intuitive idea about to help you understand why we care about the centroid. So if I take this beam, this is a beam that's supported on two supports on its ends. If I chop it and turn it and look from the side, I'm going to get a cross-sectional view of that beam. And its centroid is going to be right there. And they're showing this thing called the neutral plane. Well, what is that? It has to do with if we put a load on here, which we will, hopefully it's somewhat clear that the top, we're going to be squishing in the atoms, pushing them closer together, so they're going to be in compression. On the bottom, these atoms down here are getting pulled apart, right? So they're in tension. But if we're in compression at the top and tension at the bottom, then at some point we have to have neither compression nor tension. In other words, it has to be just fine. It's not being stressed at all. It's just like it was back here in terms of the atoms on that plane. And that is the neutral plane, which goes through the centroid. So that's another example of kind of how the centroid is relevant. Okay. Let me check. We have 30. Okay. So I am recording this. Those of you who came in late, I apologize for, I think I sent out 2 different times. Okay, so there we go. So are there any questions or comments about any of this business? Okay, well, let's go to the work I'd like for you to consider doing. So here's our Google Meet for today. Let me just briefly go to the agenda that I sent out. Yes? Okay. Alrighty, I'll go back to that. Yeah. So here's the agenda. I'll send this out by 9 a.m. every Monday morning. And for those of you who came in late, I've already talked about the MyPLTW. Shoot me an email. I'll respond to your Gmail account because I have to paste in your info rather than, I don't have it in text format, so it'll go to your Gmail account, your district Gmail account. We're doing our Google Meet. I'm going to send out a survey, making sure you can get into MyPLTW. We're discussing centroids, and then for Friday, I would hope that you would consider doing my assignment. So I'll send that out at the beginning of the week every week by 9 a.m. Monday. Finally, let's go to finding the centroid. So this takes the place of some of the assignments that are in MyPLTW. If you're on the ball, you may have already started to do some of this work, and that's more power to you. You're going to be very successful going forward if you happen to do that. But some of it I may not be collecting, but I will be collecting the calculational one. So we won't use this thing called MD Solids, which is a program that we don't have access to. And I won't have you make the construction. You'll do that in physics class if you haven't already done so. So I've got this other assignment, and here it is. First of all, before I get bogged down in the directions, I'd just like you to find the centroid of some simple shapes and then a few more complicated ones. So got a square here, and I want it with respect to the origin. You always have to specify the origin of your coordinate system. So a simple rectangle, hopefully no problem. Again, for the triangle, hopefully no problem. But I would like for you to calculate it and show your work. And then we have this figure. So this figure, hopefully it's clear to you that you can use uh, either this, probably the subtractive method, right? You would break this up into the full square and then subtract away the contributions from the rectangle and the semicircle. Now this problem, if you Google Centroids PLTW, you're going to find the solutions to this. So what I'd recommend, um, trying it up first and then taking a peek. We'll go over it next time, of course. But it's out there, so I'm aware of that. But why don't you try it on your own first? Now this one, this is a different problem that is similar, but maybe slightly more complicated. I think there are uh, four simpler areas that you would break this one into. If you're really skilled at Googling and lucky, you'll find this one as well. But hopefully you won't, so that I can see how you do on this one. So you'll find the centroid of this object by dividing it into four different um, simpler figures, and also its respect to the origin, which I've identified here. It's in metric, which is nice. And so I'd like for you to do that one as well. Okay, we're about done. So let me go through these instructions, and even if you're not interested in centroids, they don't make you giddy with excitement, you might consider this assignment as practice on doing long, not conceptually difficult, but yet messy calculations, of which you'll have opportunities to do copious numbers, many, many in the future if you continue in engineering. So why not get some good habits down now? So as you do this calculation, keep in mind that someone will have to read it. It must be clear and neat. I recommend using a pencil. Always draw a picture or cartoon of the problem first. And for these, as we saw in those examples on my PLTW, I think they drew like, 3 pictures, keeping everything nice and neat. And I'd strongly recommend that. Do the calculations in a step-by-step manner, working your way down the page. So time should flow down the page rather than having your steps sort of go wavy or in some, weird fashion. Put a bit of white space between your steps, vertical white space. You're encouraged to box significant intermediate results. For example, maybe the centroid of the simpler figures, which you're going to use later. You can even use a highlighter to highlight those. That's very useful to me, and also to you, as if you go back to use it to study for an exam. If you, we won't have, but in your future classes you will. Box the final results and don't forget the units. Okay, to turn this in, take a good quality photo of each piece of paper that shows your calculation. If you don't have a device to do that, just shoot me an email and we'll work something out. Be sure there is enough light. Be sure that you're writing dark enough to be picked up in the photo. Now I'd ask you to suggested that you use pencil before, but sometimes those don't show up in the photo. So if you're a really light writer, and I think there's some folks in this class who are, then, you may have to push a little harder on the pencil. Okay, insert the photo in a Google Doc. Be sure the photo is oriented correctly, so rotate it if it's sideways. crop away extraneous parts of the photo, parts of the paper you really haven't written on. Repeat steps 1 and 2 until your entire calculation is in electronic format. Name your file this, and then submit it to Google Classroom. So this unit that we're in is just naturally more calculational than working with equipment, although we definitely would be working with equipment if we were in the lab, um, building bridges and things like that, and pulling cylinders of brass and steel and aluminum apart. Fortunately, we can't do that, so this is going to seem a little different than the rest of the class has been to date in terms of calculations, and that's just kind of the nature of this particular unit. Okay, are there any comments, questions about anything? Okay, we still got 30 people here. That's awesome. So can somebody write in the chat, yes, I'm still here? Okay, thank you, Colin. How appreciate it. Yeah, I know it lends itself to not really jumping out and talking. Okay, well, I hope this was useful for you. If you have any problems at all at any time over the next 7 weeks, um, shoot me an email. I'm on top of email during the week and even not during the week. We can even have a one-on-one um, or maybe one-on-two Google Meets with some of your friends if you want to talk and go over some problems more individualized manner. Um, let's see, am I forgetting anything? I don't think so. I think if there aren't any further um, questions or anything, I think I'll let you guys go and not take any more of your time. So if there aren't any more questions, comments, then thanks for logging in. I really appreciate it. I'm really excited about interfacing and interacting with you guys again. Energized by it. I have a quick question about the agenda in general. Sure. Do you want to unmute, Colin? Or do you want to?
Isn't the even days supposed to be on, I think, Tuesday and Thursday, and Friday was supposed to be just kind of like a prep?
Yeah, that's right. So Tuesday and Thursday is even.
So what exactly is like the Friday work supposed to be homework or something? Is it optional work?
So according to I think you've all probably received this. So Friday we don't meet. Tuesday, Thursday is even. Monday, Wednesday is odd. So, sorry, Colin, can you repeat your question? I suspect.
Since your agenda includes stuff for Wednesday and Friday, but I thought even periods are supposed to only be Tuesday, Thursday.
Oh, I see what you mean. Okay. Okay, good point. Thanks for asking that. So what I intended to mean for that is that this is what I would see you guys working on. If you want to sort of get your bearings, okay, what should I be working on principles of engineering? And it's a Friday, we don't have class, or it's a Monday, then I would put what I think you're probably working on. Not necessarily that you must work then or that we're going to meet. In fact, we'll just have a Google Meet once a week unless there's demand for more. Does that make sense? So does that make the work optional? Well, as long as you you sort of log in, then you're going to get a pass. I'll lay it out. So I guess in that sense, it's sort of quasi-optional. But what I mean is that, again, getting back to this little agenda, on days we don't meet or aren't allocated in this little schedule, in other words, Wednesday and Monday and Friday, these are just what I think you're could be working on. And so on Wednesday, right, even though we weren't supposed to meet, we didn't, you can still be working on these things. It's just what I think is sort of what you might be doing in my class, not that you have to do it on that particular day. Okay, let's look at some of the other. Okay, So looks like not very many people want to speak. I think didn't repeat the question. I didn't repeat the question. Yes, thank you, Ryan. I didn't. Shame on me. The work is, as I mentioned, in terms of optional. I hope you don't consider it optional. I hope you try to get something out of it. When is it due? Well, I think that's a very good question, and I'll be more clear on that in the agendas. Since we're going to meet next on Tuesday of next week, which might be the 22nd, but don't quote me, that is when I'm going to go over the solution to it. So it would be due, if you don't want to see the solution, it would be due by the time we meet next Tuesday. Okay. Can I go to the bathroom? Sure. But go to the end of the bathroom first. Make sure you take the pass and sign out. I missed all this because you changed the time. Akshay, I apologize. I am recording this and I am going to publish the video and I'll distribute that as well. You were 6th was the only class I did that on, but still, that's one too many. I do apologize. You can view the lecture afterwards. I'll have the video published. Should be posted in the Google class. What time is the meeting? Okay, what time is the meeting on Tuesday? Good question. So I'll see if I can attach this little document, but I think you all have it. So we're only going to meet on Tuesdays and Thursdays at 1 o'clock. And again, probably only one of those days, probably just Tuesday, unless there is a demand for more. So we would, what time is the meeting? It'll be on Tuesday at 1 o'clock. And again, I apologize for screwing that up this time. Why are my lights off? Was that for me? Let's see. Thanks for reminding me. I had to close the window because they're cutting down a tree and I forgot to turn my light on. So I hope you were able to see me throughout that exhilarating lecture.